A very good afternoon to Professor Dr. Tanmoy Banerjee. Welcome you, sir, and very good afternoon to all of the participants present over here. So, in this 5 days FDP, this is our second day, and the first talk of this day will be delivered by Professor Dr. Tanmoy Banerjee. We'll start his talk with a brief introductions of about him. So, Dr. Banerjee is currently as a professor at the Department of Physics of University of Bardhaman. His research area mainly in nonlinear science, mostly focus on nonlinear oscillations in physics, biology and engineering, synchronization of chaos and its application in physics and engineering, open quantum systems. He has published one international book and also published 80 research articles in different reputed international journals and conferences. Under his supervisions, 4 students have completed their PhD degrees, and 6 is currently working. He was a visiting scientist of Technical University of Berlin. He has got an award for the most cited authors award in the year 2018 from Institute of Physics, European Physical Society. And also he awarded as the most trusted referee from the Institute of Physics. He is also the editor of the Journal of Physics that is named as Pramanna, and also associate editors of Frontiers of Network Physiology. He is also a fellow of the IET. So with this brief introductions, I would now request Professor Banerjee to start his presentations. Thank you.
Thank you, Dr. Mukherjee, for your very generous introduction. First of all, a very good afternoon to all the participants. And let me convey my sincere thanks to the organizers, Abhishek, Dr. Abhishek Das, Dr. Mukherjee. So thank you for having me. Now, as I think this is the second day of the FDP.
Yes.
So most of the talks will cover the application potential of the recent advancement in microwave and millimeter wave technologies. But in all those things, one thing is very ill-defined or elusive, that is the principle of oscillation. So how we do get oscillations from a circuit, from a system. So in this talk, I will go to the very basic of getting oscillation from a circuit or a system. It may be a radio frequency circuit. It may be a microwave frequency circuit, for example, GAN diode, GAN oscillator, trapet-based oscillator, or tunnel diode-based oscillator. So what is the basic oscillation principle? What till date we do know about oscillation principle, that I will recapitulate, rather discuss. Then I will introduce other things step by step. So I will keep my talk very basic, and if you want to interact during my talk, you can stop me and interact with me. Okay, let us start.
Okay, sir.
So I think it is visible.
Yes, sir. Yes.
Okay. So as you can see, the title of my talk is understanding oscillation from periodic to chaotic oscillator circuits. And to start with, for the time being, forget about the frequency ranges. We will discuss the oscillation principle in general. And also forget about the electronic circuit. We will discuss oscillation principle in general means we will discuss oscillation principle for electronics, for biology, for chemistry and physics. And we will see that surprisingly, all the physical and biological and engineering systems actually obey the same oscillation principle. So these are the points I will discuss. First, I will go through nonlinear system and why we should study nonlinear system. I will discuss. Then oscillation principle. Then we come to our own field, that is electronic oscillator, chaos, time delay system. So there are lots of topics, and let me see how much I can cover in this talk. Now, in electronic oscillator or electronic circuit, nonlinearity is inherently there. What types of nonlinearities are there, I will discuss later on, but I will show you some systems and circuits that will show oscillations. This is an example of a very popular nonlinear electronic oscillator. This is called Chua's circuit, and this is LCL circuit. And this is not a certain kind of nonlinearity. And if you draw the voltage across C1, C2 and inductor, you will get this strange looking attractor. That is in CRO, in XY mode, you can see this type of attractor. That is voltage waveform in XY mode, you will see this strange behavior. Laser, as we all know, laser is a manifestation of atomic oscillation. So a large number of atoms, they oscillate in phase and gives rise to coherent, intense electromagnetic signal. That is called laser. Josephson junction is an example from physics and engineering. It was predicted by Brian Josephson in the year 1962. These are two superconductors, and between these two superconductors, we have an insulator. If the thickness of the insulator is very narrow, then there will be some quantum mechanical tunneling, and as a result, we will get a terahertz frequency oscillation. That means you are getting millimeter wave oscillation from this particular system. This was predicted by Brian Josephson, and he got Nobel Prize in Physics in 1973 for his contribution. This is one example from biology. Fireflies, Jonaki poka, in a bush or tree flash in unison. They all are synchronized and flash in unison. So this is one kind of biological oscillator. Now the most stable oscillator, actually we carry the most stable oscillator in our body. So human heart beating exactly over 1 lakh times every day. And we can, we all know that a non-diseased or a normal heart is beating uh, 72 times per minute. And in this heart, we have some biochemical oscillators. These are called pacemaker oscillators. And we all see our ECG signal. And ECG signals are relaxation oscillation generated from heart, and that keeps the heart moving. This is one of the examples of chemical oscillations. In chemistry, it was originally believed that there will be no oscillation in chemistry, but in 60s, Prigozhin, the group of Prigozhin, and before that, the group of Belousov, Zhavtinsky, they observed okay. They observed chemical oscillations, and Prigozhin got Nobel Prize in chemistry for his work in chemical oscillator. This is the example of oscillation in ecology. Suppose we have a hypothetical jungle where we have some wolf and rabbit. So this predator and prey model is a second order differential equation, and this is nonlinear second order differential equation model. And over the time, in the span of 40 years, we can see that the population density of or population of predator and prey shows a very good oscillation, nearly sinusoidal, or it may not be sinusoidal, it may be relaxation also. So,
Sir, sorry to interrupt.
yeah,
Some participants has raised his hand, so he might be
okay,
want to interact. So may I allow him?
yeah, please.
Okay. Thank you. Partha Sarathi, you can now Partha Sarathi, you can now unmute yourself and raise your query.
I think it may be unintentional.
No,
Unintentionally, suppose is pressing the
hand raise key.
raised hand. Yeah.
Okay, still he is not responding. So okay, you continue, sir.
Okay.
এবার বের করে দেবো।
And finally, another kind of oscillation. This oscillation is also the oscillation of current voltage oscillation. This is called action potential. And this action potential is actually occurring in our neuron. This is a famous model, mathematical model. This is called Hinmarsh-Rose model. There are other very simple models, for example, Fijau-Nagumo models. Here you can see X is the membrane potential of the neuron, Y is the fast current, sodium or potassium current, and Z is the slow current, and we can get several oscillations profile from this particular equation, and that oscillation profiles actually mimic our neuronal oscillations. So what are the common factor? What is the common factor that organize all the oscillations? That is, we have oscillations from neuron, ecology, chemistry, heart, fireflies, Josephson junction, laser, and electronic oscillator. So all these are oscillator. It is not that we have oscillator in electronics only. So we have oscillators everywhere. That's why we have to learn the basic principle of oscillation. In electronics, generally we just write down the transfer function and doing some Barkhausen criteria and say that this is the condition of oscillation, this is the frequency of oscillation. But in biological oscillator, in ecological oscillator, there will be no Barkhausen criteria. So that's mean we don't know the exact principle of oscillation, and we should know the exact principle of oscillation to make them useful for applications. So all are oscillators, and the common factor in these oscillators is the nonlinearity, because without nonlinearity you cannot get any oscillator. So if you have an L and C, inductor and capacitor, and suppose there is no damping, consider a thought experiment or hypothetical experiment. So that L and C gives rise to a second order differential equation, and that is called harmonic oscillator, that we are conversant with from our higher secondary class. So although we get some kind of oscillation from harmonic oscillator, from a pendulum, but they are not natural oscillators. Why? Because they have some kind of natural frequency, but what they don't have is they don't have a characteristic amplitude. Their amplitude depends upon initial condition. So suppose we have an LC circuit or this simple pendulum. These pendulums, if you force it, depending upon the initial force, you will get different amplitude. If you force this pendulum with a small force, small perturbation, then you will get a small amplitude. So in a reliable oscillator, we must have a characteristic amplitude, and we must have as well as a characteristic frequency and amplitude. Both should be there. So those frequency and amplitude should not be dependent on initial forcing or external perturbation or noise. So that's why LC circuit or a simple pendulum, they are not self-sustained oscillators. So how to uh, define, how to model an oscillator? So any self-sustained oscillator is, in electronics and physics, we call it nowadays a limit cycle oscillation. So to limit cycle oscillators are the natural oscillators. All the natural oscillators, be it electronic oscillator or biological oscillator, they are called a limit cycle or self-sustained oscillator. Actually, this was the mathematical model was proposed and developed by Van der Poel, Balthasar Van der Poel, along with his, you may call him collaborator or student, Van der Mark. And this is a very popular Nature paper published in Nature in 1927. So in 1920s, Balthasar Van der Poel, an electrical engineer and a physicist, gave the concept of nonlinear oscillator. And the nonlinear oscillator, he proposed, the equation looks like this. So let us dig into some in a deeper way how to understand this particular equation. Suppose I have this particular equation. So X means some voltage or current. x double dot plus omega square x is equal to 0. So this will give an oscillation t versus x, sinusoidal oscillation. But you can see that there is no damping term. But in nature, there must be some kind of damping, that is loss. So this is not a natural oscillator, that is harmonic oscillator L and C. So if in nature we have perfect inductor, perfect capacitor, then only we can get this type of oscillation equation. But in nature, there will be some dissipation. So there must be some resistive term. And that resistive term gives rise to damping. So B x dot, B is the damping parameter. And we will get damped harmonic oscillation. That is, we cannot get oscillation out of this damped harmonic oscillator term. What van der Pol considered is that he considered that this damping term is itself a nonlinear term and it depends upon the value of x. So x dot omega square x. Now you can see that this damping term is not a constant term. Damping depends upon x square, bx square minus 1. And what magic it does is that suppose you consider this equation and I am claiming that I will get a self-sustained oscillation. Now you can see that if x greater than 1, then the whole term in this red box will be positive. That means positive damping. So if this oscillation tries to make it bigger, tries to diverge, then this damping term, positive damping term, or this dissipative term limit this oscillation and keeps the oscillation at x is equal to 1. Now what will happen if x less than 1? Then x square minus 1, this term will be negative. So this total term will be negative. So this is called negative damping. Negative damping means you are giving some kind of energy into the system. Positive damping means dissipation, and negative damping means generation of energy, that is pumping. So whenever the oscillation tries to become weaker, become less than 1, then some kind of energy is pumped into the oscillator system such as to keep the oscillation amplitude is equal to 1. So this is the beauty and magic of the term x square minus 1 that was introduced by van der Pol. So up to this point, do you have any question? So this is called van der Pol equation. Or we call it VDP equation. So this equation is very popular and widely used in electronic engineering, mechanical engineering, and what not. let me show you where these particular equations are used. So that particular equation that I discussed was written to model the oscillation uh, generated from this triode valve circuit. So in 20s, we got triode valve, and several experiments showed that some kind of oscillations are generating, and these oscillations was modeled, mathematically modeled by Balthazar van der Pol. And you can see that the most important term is x squared term, that is nonlinear term. And van der Pol said that without nonlinearity, you cannot model a system that gives rise to self-sustained oscillation. So in any natural oscillator, there must be some kind of nonlinearity. Although van der Pol proposed this equation to explain this triode valve circuit, later in the next year, you can see 1927, in the next year 1928, he published a paper, The Heartbeat Considered as a Relaxation Oscillation and an Electrical Model of the Heart. So he understood that this particular equation will be helpful to explain the ECG signal, or so-called relaxation oscillation of the heart. And nowadays, that particular equation is used to explain the action potential of neurons, earthquake, oscillations from earthquake, to model the right and left vocal cord or vocal cord oscillation. And recently, quantum oscillators, several papers are published nowadays, and we are also working on it, quantum oscillator. In robotics, because in robotics, the limb movement of hand, movement of several limbs, they are modeled by this van der Pol equation. So in robotics, for limb movement, there must be some local oscillators, and those local oscillators are designed, implemented, keeping in mind of this particular equation, this simple looking equation. And obviously, due to this x squared term, this particular equation is nonlinear equation. So this I already discussed. Now the problem was that for the last 100 years or so, whenever nonlinearity came, we just ignore it. We used to ignore it. We take linear approximation. It may be in our concept of transfer function. It may be in our concept of input-output relation, gain, Barkhausen criteria. So we always love to play with the linear system. But as I discussed, there will be no oscillation in linear system. So all our knowledge of linear system cannot provide sufficient insight to understand natural oscillators, let alone the electronic oscillators. So for the last 100 years, we used to ignore it. But nowadays, we now know that we have to consider the nonlinearity. We have to live with the nonlinearity in order to understand oscillations. And these days, we know that dealing with nonlinearity is not a big deal, actually. What we used to believe that it was very difficult, it was very complicated. That is not the case. There are several techniques. Using those techniques, we can get some insight into the nonlinear systems. So our task is to understand oscillator as it is, to understand the nonlinear oscillator using nonlinear principles. Don't try to linearize it or other things. Now, suppose you have, I'm not going into the mathematical details. So suppose you have a simple first order equation. Suppose you have a circuit that consists of R and C. So if a circuit consists of R and C, you will not get any oscillator. So this is called first order circuit. First order system or circuit. Why first order? Because we have only one storage element in the form of C. You may also use L. And why this is called first order? Because the current voltage equation is a first order differential represented by a first order differential equation. So we all know that no first order system can generate oscillation. So to get oscillation, we need at least second order system. That is, we must have at least two storage elements, two capacitors, or one capacitor, one inductor, etc. So at least two storage elements are required to get oscillation. So if somebody asks me, suppose I want to design an oscillator, what are the essential building blocks of an electronic oscillator? My first answer should be there will be some active element. That is, active elements means it must have some amplifier. Since we are designing some oscillator, so there must be some characteristic frequency. So we need frequency selective network. Number three, there must be some positive feedback. Actually, positive feedback is a mean of inducing negative resistance. So in the case of GAN oscillator, in the case of impact-based oscillator, impact trapet oscillator, or tunnel diode oscillator, all those microwave oscillators, they rely on the negative resistance. So negative resistance means something is being generated, some power is being generated. So without giving anything, you are getting some energy. And so it is very general to write that we must have some negative resistance. And one more thing we require, and that element is not discussed in our textbooks, but we must mention it, that is nonlinearity. Without nonlinearity, no oscillator is possible. So any electronic oscillator, be it radio frequency oscillator, for example, RC, LC oscillator, be it microwave frequency oscillator, be it GAN oscillator or other things, or be it millimeter wave oscillator, we must have these four elements, four blocks into those oscillators. And don't forget nonlinearity, because up to this point we understand that nonlinearity is a must. Okay. Now, what I cannot create, I do not understand. It was said by Richard Feynman. And let us take a very simple real life example. And that example is this. Can you identify this particular circuit? Okay, this circuit is the circuit of Venn oscillator. Venn oscillator, you can see we have an active device in the form of op-amp. We have positive feedback here. We have frequency selective circuit, R and C. And where is the nonlinearity? Nonlinearity is actually coming from the op-amp itself. How? Because op-amp tries to limit the voltage. If we use a non-inverting op-amp, then this portion is linear, but after that, it gets saturated. So if somebody tries to go beyond this point, op-amp will limit it. So this is called limiting type nonlinearity. Limiting type nonlinearity is provided by this op-amp. Now, in our textbook, what we did up to now, we write down the transfer function considering this RC circuit, and in the transfer function we have real part and imaginary part, and we play with those real part and imaginary part, and we got the condition of oscillation and frequency of oscillation. Now let us try to consider this particular Venn oscillator as a real-time system like our heart, our ecological system, or neuron. So there are some voltage levels. Vc1 is the voltage across this C1 capacitor, and Vc2 is the voltage across this C2 capacitor. Now the general principle is try to write down a differential equation of this circuit. So we C1 dVc1 dt, that is voltage current through this capacitor and current through this C2 capacitor. So using KCL, you can write this. I will explain only one line. Suppose you are trying to find out current through the capacitor C2. So current through capacitor C2 is C2 VC2 dt, where VC2 is the voltage across the capacitor C2. So this current is equal to the current through this R2. So current through R2 means voltage here V0 minus Vc2 minus Vc1 divided by R2. So this is the simple KCL equation, and from this KCL equation we are getting the first order differential equation for capacitor C2. Similarly, we can get another differential equation for capacitor C1, and this is the final equation. So in differential equation mode, you can see that this is a second order system. So that's why we are getting two first order coupled differential equation. So these two first order coupled differential equations we have now. And the condition of oscillation will be the trace of the matrix will be 0, and frequency of oscillation you will get by finding out the determinant of this matrix. So ultimately, if you can establish, you can derive the differential equation of any circuit, any system. It may be electrical circuit, it may be biological circuit or system. So if you are able to find out the differential equation, from that differential equation, you can get condition of oscillation and frequency of oscillation by finding out the trace of the matrix and determinant of the matrix. So there will be no need of Barkhausen criteria or other things that electrical engineers used to rely upon. So using this, you can see that the well-known condition of oscillation, that is Ra is equal to 2Rb, we are getting. This is another well-known example. This is actually a bandpass filter. What is the order of the system? This is the order of the system is second order. We have two capacitors, two storage elements. So this is a bandpass filter. So in this bandpass filter, we have some kind of frequency selective network. We have positive feedback, and we have active device. And also this will act as nonlinearity of amp. So if we can tune it, we can get some kind of oscillation out of this circuit. This is the differential equation. This is V0 and this is V1. We have got two coupled first order differential equation that is equivalent to second order differential equation. So dV0 dt, dV1 dt. So these are the circuit parameters. And condition of oscillation is this plus this, that is diagonal elements. Their summation is equal to 0. That gives rise to the condition of oscillation, and frequency of oscillation you can find out from the determinant of the system. So you can get condition of oscillation and frequency of oscillation. So this is how, in general, you can take any system, any circuit, find out their differential equation, and from that differential equation, you can get condition of oscillation and frequency of oscillation. So this is the general principle of oscillation. You don't have to use any approximation, Barkhausen criteria, all those things. Now, up to this point, we restricted our discussion to second order differential equation or second order system. So first order system, does not show any oscillation. To get oscillation, we need at least second order differential equation or second order system. But second order system can give only self-sustained oscillation, but more complex oscillations we can get if we consider three-dimensional or more than 3D third order system. So in third order system, things are getting complicated, and we have a new kind of oscillation that is called chaotic oscillation, which is of much interest in the last 2 decades. And people are still trying to understand and to try to apply the concept of chaos in secure communication system, cryptography, etc. So what is chaos? Chaos is, without getting into much more mathematical jargons, chaos is defined as a long-term aperiodic signal or long-term aperiodic behavior shown by a deterministic system which shows sensitive dependence on initial condition. So there are several terms in this particular definition. Let me decode those terms step by step. What is deterministic system? Deterministic system means the systems that have mathematical model. If you can write some mathematical equation of a system, that system is deterministic system. And there is another kind of system that is called probabilistic or stochastic system. In probabilistic or stochastic system, you don't have any mathematical model, but you have statistical model, that is probabilistic model. So noise is an example of stochastic signal, but chaos is not stochastic signal. It comes from deterministic system, but its long-term behavior is unpredictable. So what is strange? The strange thing is that a deterministic system becomes unpredictable. So noise, it is understandable that we cannot predict it because it is noisy, it has some probabilistic distribution, etc. So that is fine. But a deterministic system, we have all the equations in our hand, we know all the parameters, but still we cannot predict chaos. That is the strange thing. The notion of chaos was the modern notion of chaos was first observed by Edward Lorentz. He was trying to predict or model some kind of mathematical equation, trying to give some mathematical equations that can model weather prediction. And that in those days, in 1963, this model was proposed. In those days, there was no personal computer, but Lorentz was lucky to have one in his office of weather office, and he reduced the 12 order system to a third order differential equation. This is the third order differential equation that is written in terms of 3 coupled nonlinear first order differential equations. So this third order differential equation, you can see this type of oscillations are coming. So in time series, it may appear that this oscillation is noisy, but if I draw x versus z, then x, y, z, then you are getting some kind of strange behavior in phase space. This is called strange attractor or Lorentz attractor. So this is chaos. So if in the periodic case, you can have a circle or ellipse, but in the case of chaotic signal, in the Lysage's figure, you have this kind of strange behavior. So in real time, it is very much unpredictable. You cannot predict it. But in phase space, it is bounded in a geometrical manner. And that geometry is very complex geometry. Now, the chaotic system was proposed by Edward Lorentz, and after that, in 70s, Otto Rosler proposed another system. But apart from computer screen, people were not able to observe chaos in laboratory. In 1980s, Leon Chua proposed an circuit experiment, and that electronic circuit is very flexible. You can design it, implement it in your breadboard. You can observe the voltage waveforms in simple CRO. Lysage's figure gives rise to phase-space trajectory. Real-time figures you can also observe in the CRO. So in 80s, Leon Chua proposed Chua circuit that proved that chaos is not a mathematical abstraction or numerical errors, but it has some existence in real life. Now, the problem was that till date, we don't know what are the sufficient condition of getting chaos. So suppose if you want to design a chaotic circuit, you don't have any prescription. That is, just do these things and you will get chaotic signal. Because till date we don't know sufficient conditions of getting chaotic signal from a circuit, from an oscillator. But what we what we do know is the necessary conditions. What are the necessary conditions? That the circuit should be of third order or more. Should be some kind of nonlinearity. So these necessary conditions we know. So that's why if you design a new chaotic circuit till date, that circuit will be, your paper representing that circuit will be accepted in good journals. So this is a very hot topic of research. So if you are interested, try to propose some kind of new chaotic electronic circuits and you will get some publications. So what is the research in this field? Design of simple and well characterized chaos and hyper chaos is a good area of research because we still don't know the sufficient condition of chaos generation and study of their synchronization. Suppose you are observing chaos in a circuit. If you want to apply that chaotic signal, you need to study the synchronization, how they behave in transmitter and receiver. You have to receive it. You have to demodulate some message signal from out of the chaotic signal. So all these things are very hot topic of research. This is chaos in electronic circuit. This is one of the examples. Many circuits we have invented in our lab. This is one of the examples where I implemented, or I first proposed Chua circuit. In Chua circuit, inductors are indispensable, but what I proposed that inductors are not very efficient in the low frequency range because the size of inductor would become larger, and inductors are always accompanied by some kind of resistors. So in all the inductor based circuits, particularly in the low frequency range, people uh, tries to avoid inductor. In this circuit, we avoid inductor by using band pass filter, active band pass filter. So this is the circuit, chaotic circuit. And if you ask me how did you arrive at this particular circuit, actually that I cannot tell you because we don't know sufficient condition. So it is type of try and error things. You must have three storage elements. You must have some kind of nonlinearities, but what kind of nonlinearity you should have used, that we don't know. It is kind of try and error method. So this is the mathematical model. So this I am showing because this is how you have to establish your circuit. Just designing some circuit in breadboard and showing their waveforms in the CRO, that will not suffice. You have to show the mathematical model. You have to show the numerical results. So this is the third order differential equation I have derived from this particular equation. This is V0, V1, and V2. And believe me, apart from KCL and KVL, to arrive into this equation, I don't need anything. I know these very basic things, KVL and KCL. Now, this mathematical model is in the term of voltage and current. And you can see there are capacitors values are of the order of nanofarad, 10 to the power minus 9. Resistors are of value of kilo ohm, 10 to the power 3. So there are order of difference in the numerical values of C and R. If you try to run this equation in your computer using C program or Python, you cannot do this. You have to make this equation dimensionless. So this is the dimensionless equation. So now we have in our hand a third order differential equation, and using say Runge-Gupta 4, RK4 in Python, C or MATLAB, I have got this Lissajous figure, X versus Y. And as you can see that if I change some parameter R1, some resistance, this is a single loop, this is a double loop. This is so single to double to 4 to 8. Then this is chaos and this is also chaos. This is called period doubling root to chaos. So all these things, so this is X versus Z. And now these are the experimental waveforms or Lissajous figure I have got from CRO. So you can see, observe the agreement between the experimental results and numerical results. So you have to show the agreement between numerical and experimental results. So this is chaos. chaotic attractor. So these are numerical plot generated from computer, and these are generated from our real circuit. So these are some more chaotic Lysage's figure I implemented, I have invented in our lab. And apart from its scientific value, we can always see it has some aesthetic appeal also. So you can realize or feel the complex geometry it is in the phase space. I think I have some. Okay. This particular chaotic circuit is widely used in these days in various universities in the master degree lab. This was invented by my group in 2010. And in our lab also, uh, students, MSc students, they used to design this circuit and feel the rhythm of chaos.
আস্তে আস্তে ঘোরা
লক্ষ্য করে দেখতে পাচ্ছ এটা this was taken by our master degree students, and this is period doubling, period 4, and this is chaos. So you are observing a strange thing using very cheap simple circuits and a simple CRO. So this is period 1, that is limit cycle oscillator, but in 3 dimension much more can happen. So it may happen that you can get period 1 to period 2 and then chaos. So this is chaotic attractor. We call it chaotic attractor. So this is nothing but chaos, the Lysage's figure of chaos. This circuit, you can suppose you have this Lorentz equation. In this Lorentz equation, you have x dot, y dot, and z dot. If you can use 3 integrators, you can easily generate chaos, or you can easily implement this Lorentz equation in electronic circuit. And this circuit was implemented in our lab, and this is the Lysage's figure, x versus z. So although these things are very hot topic of research, but you don't need a very sophisticated laboratory, very high-ended laboratory to design or implement these things. So those who are working in colleges don't have sufficient funding. You may, if you have passion, you can always try your luck with these chaotic circuits. This is the real-time behavior of Lorentz system. So it looks like a chaotic noisy signal, but in Lysage's figure, it is governed by some kind of strange geometry. Okay, up to this point, I discussed equation, that is systems that doesn't have time delay. The main problem of high frequency electronic circuits and systems, for example, in terahertz or microwave region communication system, the signal needs some time to reach a particular destination because of the finite propagation speed. So a finite time is required to reach a particular uh, receiver or destination. So due to finite processing time, due to finite propagation time, time delays are everywhere. So in those high frequency circuits and systems, it may be a communication system or processing system. So there are time delays, and time delays are dangerous for these high frequency systems. Why dangerous? Let me give you an example. Suppose wait a minute. Suppose you have an equation, a system x dot is equal to kx. So x is a function of time. This is also a function of time. This is a first order equation, and there is no oscillation, as I discussed. And but if there is some kind of time delay, then the derivative will depend upon the value of x at a previous time. So there must be some history function. So time delay makes this system infinite dimension. So a little bit of time delay makes it infinite dimension, and you are getting chaos from three-dimensional system. So you can easily understand what complicated things it may show, because now we have infinite dimension. So due to finite propagation system time or finite processing time, we invariably have some kind of time delay, and that time delay makes a system infinite dimension. And that's why in the high frequency region, you must be very aware that how to control that time delay, how to avoid that time delay. I'm facing some problem, please pardon. Okay. Surajit or Abhishek, is it visible?
Yes, sir. So it is visible completely.
Okay, but okay, some kind of okay. Now it's working. How much time do I have? 10,
Sir,
5 to 10?
sir, okay, no problem. Sir.
Okay, now, so all these things, suppose you have a first order system, a simple R and C circuit. This is R and C circuit. Now, if you, in the feedback path, if you allow some time delay and control this time delay, then you can introduce a higher order dimensionality, and this simple circuit can give this type of chaotic signals. This type of chaotic signals. Now, why should we, as engineers, should we bother about chaos? So what are the applications of chaos? So chaos are widely used in communication, that is secure communication system and cryptography. So suppose I have an input signal, there is some kind of modulation, and the carrier signal is used as chaotic signal, and then transmit it, and you will receive the chaotic signal here. And if you can able to synchronize this chaos using a chaotic receiver, then you can receive the proper or appropriate signal. But why it is called secure communication system? Let me explain. This chaos-based communication system was it was commercially implemented in Athens, Greece, and it was reported in 2005 in Nature. And they encode the message with the help of chaotic signal, and transmit it over a 120 kilometer of optical fiber in the metropolitan area network of Athens. And they achieve the corresponding bit error rates below 10 to the power minus 7. So they found that chaos is actually a very good mean of communication. So this is the map of metropolitan area of Athens. This is the fiber link. The total communication was implemented using chaotic signal. Suppose this is the input message signal. It is taken from their Nature paper. This is input message signal. And this is transmitted signal. In the transmitted signal, you can see that there is no trace of the input message. So transmitted signal looks like a noisy signal. So any unauthorized user cannot suspect that this noisy signal actually carrying some kind of a message. So the chaos-based communication is secured in that sense because no unauthorized user can illegally demodulate or retrieve the original message signal. And this was the decoded message signal in the receiver end. So chaos-based communication relies on that security aspect. And in these recent days, people are trying to get optical chaos-based communication system. This one was published in 2018, and there are huge number of research going on that works in chaos-based communication system. And these days, people are trying to increase the bit rate. You can see that this 30 GB per second bit rate they are achieving. Now, with these brief things, I should conclude because it's almost time. But before I conclude, there are two types of science. One is big science. It costs a few million to $billion. Its time period is of decade. A decade of effort is required. Thousands of scientists working on this big science. For example, Large Hadron Collider, satellites, 5G technology. All these things are big science. You cannot contribute to it with your limited infrastructure or all those things. So big science requires big infrastructure, and there is another kind of science that is called hands-on tabletop science. And hands-on tabletop science requires only one or two CROs, some breadboards, an inexpensive computation tool in terms of your laptop or desktop. So with this, you can actually contribute to this nonlinear science. So nonlinear science means understanding of nonlinearity, understanding of oscillations, chaotic oscillations. You can propose schemes to encrypt your data using chaotic signal. So all these things, these are in your reach. You can contribute into this. So with this, I should stop here. And if you are interested, you may always contact me through this email. So thank you very much.
Thank you, sir. Sir, I have one question. Sir, you told that is the chaos can be used for the secure communication. Sir, for secure communication, we can also use the spread spectrum.
Yes.
So which one is better, sir? That is the chaotic communication system or sir spread spectrum?
Yes.
And another thing that is you told that is the chaotic system. That is we cannot. That is at the receiver end. We cannot means that when the signal is transmitted from the transmitter side, sir, at the receiver end, how we decode that modulated signal. That's because you told that is the we cannot means the implement the chaotic system. So how you can decode the system at the receiver end, sir?
Okay, okay. Very good questions and very relevant questions. First, let me answer you the first question. That is speed spectrum. In the speed spectrum signal, although it is speed spectrum, although it is generating some kind of pseudo-random sequences, but there are some kind of clocks. Some clocks are required to generate speed spectrum signal. And you cannot, in the spectrum, you cannot get rid of those clocks. So speed spectrum is not completely unpredictable. But in chaotic signal, the chaotic sequence, if I have, in the chaotic signal, the spectrum is very broader than speed spectrum, and that spectrum does not contain any kind of spurious clock frequencies. So in that context, nobody can intercept chaos without the knowledge of its circuit parameters. And the second question is difference between chaos and noise. Noise is probabilistic. That's why noise cannot be synchronized. So without synchronized, you cannot get noise-based communication because noise cannot be synchronized. But since chaos is coming from a deterministic system, and although it is unpredictable, but there are some techniques using which chaos can be synchronized. So in the receiver end, if you design a chaotic oscillator that is identical to the transmitter end, and chaos is also initial condition dependent. So if the transmitter or in the transmission section generates some kind of initial condition, and that initial condition can be treated as password. That password is given to the subscriber. So any unauthorized user cannot demodulate the signal unless or until he or she got that password. So in single sentence, chaos is synchronizable. That's why we have some techniques of synchronization, and using that synchronization technique, chaos can be or message can be demodulated from that chaotic signal.
Okay, sir. Thank you, sir. If participant have any question, they may ask.
Sir,
Yes, please.
you have shown some open source software on the last slide.
Yeah.
So can you share the name of those software through which that we can, for the software is for simulate the circuit or to view the chaotic output which are showing in the CL?
Open source software we have used it for computation purpose. C, Python, those
Okay.
are fine. And for simulation purpose of circuit, LT-SPICE you have.
Okay.
LT-SPICE is open source software.
Okay.
For nonlinear systems, there is an XPP-AUT.
Okay.
XPP-AUT. XPP-AUT can computationally solve any differential equation and can show a lot of things without writing any program.
Okay. Okay.
Yeah.
Thank you. Thank you.
So I think that my
Yes.
talk is covering somewhat very basic things. So
Yes, sir. Yes, sir.
yeah,
So, some other questions from one participant. The question is there any possibility of generating this kind of signals using digital ICs like flip-flops?
yes, very nice question. If you simply Google search, you can find that there will be some Boolean circuits using NOT gates or flip-flops. You can get chaotic sequences, chaotic square wave sequences, not square wave, rectangular wave sequences.
Okay, as any more participants have any questions, you can raise your hand. Okay, Vivek sir.
Okay. If participant have any question, they may ask to sir. I already unmuted them.
Okay, Vivek sir, we think we should conclude. Vivek sir, please conclude.
Okay. Thank you, sir, for your valuable sir, talk. Or your talk was very informative. Thank you, sir, once again for giving you your valuable time from your busy schedule, sir.
Thank you. Thank you
sir.
very much, Abhishek. Thank you. Thank you for having me. Okay, then thank you all. I'm leaving, Abhishek.
Okay, sir. Thank you.
Thank you. Thank you.
Okay, so the participants, there will be a short break between these two talks. That is for about 10 minutes. We'll start at exactly at 4:15. So within this short period of time, you will take a bio break. You may take a tea break. So please join at 4:15. Thank you. Dear participants, there is some problem. Okay, so just have joined our next speaker, Dr. Tanmay Sarkar. He has just joined. So we'll start its presentations with some brief introductions about him. So good afternoon, Dr. Tanmay sir.
Hello.
Okay, yeah. You are audible.
Yeah, now it's audible.
Yes, sir.
Okay. Good afternoon.
Good afternoon.
And can you able to see my video also?
Yes.
Okay.
Your videos also.
Thank you.
Okay. So Dr. Tanmay Sarkar received his master's degree MTech in microwave engineering from Department of Physics at the University of Bardwan. and his PhD in Electronics and Communication Engineering from Mizoram Central University. He started working as a scientist at Summit, Chennai in 2008. He has experience in designing antennas, EMC parameters of components, antenna placement on large platforms and other areas. He also collaborated with IISc Supercomputer Education and Research Center in Bengaluru to develop an in-house code development program for IISc Summit collaborative project. He has he started work as a scientific officer, selection grade at the Radionics Laboratory, Department of Physics, the University of Bardwan, and in 2011. And since then, he's associated with the same university. He has been involved in teaching and administration in different academic activities of this department. He has published more than 30 research articles in different international journals and conferences regarding the computational electromagnetics, microwave engineering, and broadband and multiband antennas, and EMC, also wave propagations. So with these brief introductions, I'd like to hand over this session to Dr. Tanmay Sarkar. So, sir, please.
Thank you. Thank you, the organizing committee. So, good afternoon, all the participants and all the respected person here. So, today I'm going to give a lecture on this or the basic of this antenna and our this new upcoming 5G technology. So, how we are using this antenna, which kind of antenna it will be suitable in this upcoming 5G. So, this uh, the antenna, so which kind of antenna and what is the character of this antenna that can be useful for this our upcoming our 5G communication technology that I want to discuss. So just I want to share my presentations. Okay.
Yes, sir, visible.
Is it visible?
Yes, sir. Yes, sir.
Okay. Okay. Thank you. So today, my topic is antenna and 5G technology. So these are the content that today I want to cover in this lecture. These are the antenna basic, uh, the radiated by accelerated charge, sources of radiations, types of antenna, radiation from a dipole antenna, antenna parameters, microstrip patch antenna, 5G communication technology, and conclusions. So, so what is antenna? So antenna is a transition zones between a guided wave and an open wave and vice versa. So it is also defined as a transducer which converts guided wave in free space wave. So actually we want antenna for wireless communications. So and also the it should be a long distance communication. But nowadays our like our as per applications and all, we are day by day we are changing that, but near to that field also we want this wireless communication like our Bluetooth, Wi-Fi. So these are a little bit very closer to that, but still this wireless domain, it's a very advantage, like anytime we can make this arrangement. It's not required any dedicated positions, it's not dedicated path or anything. So day by day this wireless domain, this wireless communication is very popular in that upcoming technologies and all. So in IEEE standard defined a means of radiating and receiving radio waves. So first antenna was developed in 1888 by German physicist there's Harj, that we already know about him. So just wait. Yes, blessed, or just a minute. Yeah, yes, coming here. Okay. So it has displaced, that's why it's not coming. Okay. So if you see the total impedance of this antenna, this is called, here I'm written that ZA, that is RL plus RR plus JXA. So this RL and RR, this is a totally in resistive in nature. So this RL is the conductor or dielectric loss associated with the antenna. So if the antenna, which material you are using inside the antenna, if any dielectric or anything, it will be there. That losses, that then RL will get all kind of losses here. And the RR is called the radiation resistance. This is an hypothetical resistance that will dissipate at an amount of power equal to the radiated power. So how much radiated power you are getting, so from that you can get the RL. So this RL and RR is totally, it's nothing but a totally pure resistive in nature. But this JXA part, this XA part, this is the imaginary part of the impedance as with the radiated by the antenna. So this imaginary part, it's nothing but a reactive in nature. So reactive in nature means it may be capacitive or inductive. So if this reactive component, what is the nature of this reactive component? We know that if the capacitor inductor, it's like a storage of energy, like it will, you want to store some energy. So if in the transmission line, when you are feeding the antenna, that time if any storage kind of things, it will come, so it will not allow to radiate in the next stage. So if you want to just emit, or if you want to minimize this JXA part, then you will get a good antenna. So if you see a dipole antenna, lambda by 2, it's a dipole antenna, it's one type of wire antenna. It's a, if this reactive part, it will be more, so it will look like a very, it's like a storage elements, like if how the storage element it will make, when you send some power in that antenna, if it will not matched, then it will reflect back, or this is a standing wave will form. When a pure standing wave will form, that time the reflected wave will equal to the incident wave, and it's look like a resonator circuit or resonator. So it's the resonator, it's a storage like of energy, storage kind of activity you can get. So it will not pass, so it will block that signal to pass, like, so when you're sending a signal from this side, it will not go to that in that air. So if you see the dipole antenna impedance, it's coming 73 plus J 42.5. See this 42.5, that part you need to suppress, then only you will get a good antenna. So now how our antenna it will radiate. So so what are the effects and what are the things that what is the main things that a radiation will occur. So if you see an electric charge, that's an either positive or negative charge, that electric field lines radially extend from this charge to infinite, or from infinite to that charge. If it is a positive or negative, it will be changes. The pictures is showing that electric field lines is going upward, or if it is a minus, it will going in the, it is coming in that in that source side. So if this electric charge, it's a slow moving charge, its a velocity approaches to static charge, means below the velocity of the light, and its light is very near to the static charge. In that time, that figure 4a, it's showing that the electric field lines, like the field lines, how it's look like. But when you just make it very fast moving for this charge, so at that time, from the principle of relativity theorem, that electric field lines just converge in that upward and the downward directions, where we can see from here in this side and this side, it is getting converge. But if it is an accelerated charge, like in accelerations, if you give an acceleration movement in the charge, so it's create field lines, electric field lines bend and creates a transverse components. So this transverse components, once it will you can make, then only you can get a radiation. So how, I'll show one by one. But main thing is that when the acceleration, when you put in that in this electric charge, then only you can get this kind of bending in nature in the electric field lines. So now look at this picture. So here I have drawn a observation circle. So in this observation circles, if you see that that white dot, it's a static field lines at the beginning time, and after that accelerations, that its position in the other directions, and both are it's showing that both are the electric field lines also it's showing here. But if you observe that this the initial positions, and that after accelerations, the two field lines are, it will be different, that we already know that it will start bending. So why that bending? Because that it want to just a line associate with the end and the initial position. So for that this kind of bending things, it's called the kins. So this kins lines will form. So once the kins line, actually it want to connect with the initial positions. So we were just at that observation circles, we can get this kind of kins which will form. So this kins, it's nothing but a transverse component of the electric field lines. So if you see this in figure 7, as it is an AC in nature, so the observation circles, it is getting smaller to bigger, smaller to bigger. So all the transverse components is getting out from the source in different time. It's like in figure A, the time t1 and this t2 is greater than t2 and t3 is greater than t2 and t1. So so like that, this figure, so this transverse components is moving out from the speed of light, and it's create the radiations. So in that animated picture you can get this, that how the accelerated charge, how the kins are forms, and the fields are getting out from the charge. So here you can see also here, it will yeah, it will run. Is it visible? Hello, is it visible?
Yes, sir.
Okay. So how the kins is coming, and this transverse components is coming out from that electric charge. So it's create the radiations. So for create radiations, one thing is that you need accelerations. So once the accelerations will come, then only you can get this kind of radiation from a source. Okay. So in our in different origins, we can get this kind of accelerations. So where the accelerations will come, when that radius we are changing from a bigger radius to smaller radius, or from smaller radius to smaller bigger radius. If you connect one wire and you are sending a signal, that time there is a accelerations. So it will create accelerations. If there is an impedance discontinuity, so that time also accelerations will come. If there is a bend, that is also exhalations and car and reflection from the open end. So these are the different origins, so from where we can create the accelerations. So once the acceleration we are making, then you can get a radiation from the source. So in antenna, so you have to make this kind of acceleration to create radiations. So when we can observe that if coaxial cable and TV cable operators and all, if they are not fixing that cable properly, so that time we can get some kind of signal in our TV. So that is also like that is due to that open end, or due to maybe it's a bend, or it's not properly matched. So due to the reflection impedance discontinuity also, you can get so signal. So when two wire in the RF signals, when you want to connect, so it should be properly connect, otherwise there will be some radiations, and radiations, there is a power loss in your system. Okay, so this radiations on radiations, how the radiation will come, and how we can minimize the radiations. So this how the we can minimize the radiations. The EMI-EMC, that is one that it's called that electromagnetic interference, electromagnetic compatibility. So those who are dealing with this EMI-EMC, they are giving some CFCC certification, so that your device that radiations is very good, like it will not harm to the your other equipment. So they are getting some kind of CE or FCC certifications. And so this EMI-EMC engineer, they are doing this kind of activities. So this EMI-EMC engineer, they want that how the radiation we can minimize. But in antenna engineers, they want more radiation and more radiation. But the main thing is that how the radiations will come, both the engineers or both the researcher, they want this activities, that how the actual the radiations will come. So if you know that what is the how the actual radiations is coming, then you can easily minimize this things. For if you have a EMI-EMC engineers or researcher, for antenna you can increase its that radiation that you want more and more. So next is the types of antenna. So in antenna, there are different kind of antenna. So we can categorize this antenna in a different way. So first it will come that wire antenna. Actually this wire antenna made of wire only. So dipole antenna, its length is lambda by 2. Lambda is it's the wavelength. So which frequency it's operating, C equal to F lambda. So which frequency it is operating, from that you can easily get that lambda how much will come. So this is the popular dipole antenna, this lambda by 2 dipole antenna, its length is lambda by 2. Another is monopole antenna, its length is lambda by 4. Actually this lambda by 2 to lambda by 4 antenna, monopole antenna, having some advantage as a, like its gain is little bit more, and constructional point of view it's a stable, like in rooftop antennas on all, in rooftop on the car, you can get this kind of monopole antenna. So you can easily, because that car surface, that it will act as a ground, because it want a ground plane. But in dipole antenna and all, in another structure we can make this kind of dipole antenna. But in rooftop or in car top antennas, mainly monopole antenna, it will be very popular. Next is loop antenna. It's look like a loop. It's here I'm showing the circular type, but in coil loop also it will be there. So and it is also made of wire. And another is a helix antenna. This look like a helix. So this is helix antenna. It's a very useful antenna, and it's like, it's one thing is that it's called the polarizations, that CP antenna, circularly polarized, we can easily get from the helix antenna. I will discuss this polarizations later. Next is aperture antenna. This aperture antenna, it's a horn antenna. It's a very famous antenna. It's this pyramidal horn, conical horn antenna. Conical horn antenna we can get in the our DTH antenna. This is a conical horn antenna, and it's very high power. Its gain is very high, and for high power applications and high frequency application, mostly this horn antenna are using. Okay. Next is planar antenna. It's planar antenna means it's on the plane surface. So this microstrip patch antenna is a very popular antenna because it's have different advantages compared to the other kind of antenna I'll discuss little bit in the microstrip patch antenna. And another is antenna array. When a single element antenna is not able to do all the specifications or what the requirement of our requirement, like we want more gain, we want a beam steering, we want a narrow beam, so a single element antenna it can't get. So that time we can make some array and you can get all kind of activities like beam steering. Like if you want to steer the beam, it's very difficult to steer the total structure. Instead of if you steered only its beam, then it will be very easy to track the hostile elements. So here in that picture you can get that when the scanning is coming to that hostile aircraft, so you can get maximum power in some degree. So from this graph we can easily get that in 270-degree and hostile elements is coming. Okay, so next is the dipole. In popular wire antenna dipole, so how the radiations is coming. So you can see that when you're sending a AC signal in a lambda by 2 dipole antenna, so there are different time instant on where that maximum and minimum voltage you can get. So one by one you can see from that and figure A17A, you can see that when it is at t equal to 0 time, this is the charge distribution on that this dipole antenna. This is then the plus and is the minus, and it's a very little bit. And this is the feed lines coming from plus to minus. This is the one feed lines. Suppose actually it's not like one feed line. Just for understanding, we are making this kind of just I'm showing here that one feed lines is coming. So next, when it is coming at t by 4, so you are getting a maximum charged, positively charged and negatively charged, and the feed lines also it's getting more. And we can assume that this feed lines is situated up to lambda by 4 distance from that antenna. Okay, so when it's going down that as is AC signal, so this is the t by 4 plus, so all the charge distribution for this high peak is coming. So now it start that another, then in the reverse side this kind of field is coming in the reverse directions. So when it's going down, that number of field lines also it is getting more and more. So when it is at t by 2 minus, here you are getting, look, 3 number of lines downwards, 3 number of feed lines upwards. Okay, so and due to this lambda by 4 distance, now it's lambda by 4 plus lambda by 4. This is the lambda by 2 distance. This the, so we are supposing that total lambda by 2 distance, this all the field lines is like at is lying like at t by 2. So at t by 2 what will happen exactly, that 3 number of lines is upward and exactly 3 number of lines is downward. So it will make this kind of loop. And this is the on the surface of that in that on this dipole antenna, it is totally neutralized. You can get as it's neutralized, so it will just leave, these loops are leave from this structure. Okay, so the next cycles again that this thing it will happen and it will push this loops, and this loops coming out from the dipole. So look here that on animated pictures I am giving here, this how that radiations is coming from this lambda by 2 dipole. Okay, so next is the antenna parameters. So here I am I will discuss some few antenna parameters because other things also have to discuss. So first things is that the radiation patterns and lobe. So this antenna radiation patterns and lobes, it means that how the power is distributed on the or near to the antenna surface. So in the different space, so how the power is distributed. For if you know the power distributions in near to this antenna field region, in that way you can make your arrangement that in which way you can communicate with your you can make your communications. So which side you will keep your the receiving antenna, on which side you will keep your transmitting antenna. So a mathematical functions or a graphical representation of the radiation properties of the antenna as a function of space coordinates. So various part of this radiation pattern is it's like major lobes, minor lobes, side lobes, and back lobes. Look in this polar plot. This is the where the maximum power you are getting is the major lobes, and these are the small one. The side one is the minor lobes. Minor lobes. These are the side lobes, and in the back side it's called the back lobes. So all are minor lobes. So some the position of this minor lobes we can make it we can tell like a back lobes and side lobes. And one important thing is that that is a half power beamwidth, this HPBW. This half power beamwidth is nothing but so how much the maximum power is there. So from that you can go to that power where you will get a half. So in dB scale, you are generally tell that this is the 3 dB down. So how much maximum power you are getting here, and you go to the downward to that half power, and where you will get this kind of angle. This is called the half power beamwidth. So what is the significance of the half power beamwidth? So when actually this angle is showing some in some region. So in this region, if any communication you can make, so you can get a very good signal. But in other position also you can get the signal, but it's not that much. But if in this region in 3 dB sorry, in this half power beamwidth region, in this angle, what all the receiving device or transmitting device, it can communicate with this antenna very properly. So in half power beamwidth, so if it's a half power beamwidth is 120 degree, so if you want to cover an area like in mobile BTS tower, so 3 antenna is sufficient. If it is a 30 degree 3 dB beamwidth, then you have to calculate the how many antenna is required. So in that way you can see in that in cable operator they having some company having three number of BTS, some number company having the 6 number of BTS in their mobile tower. So that is their half power beamwidth how much for this antenna. In that way they have calculated. So here in figure 90, it's a linear plot. Actually, some analysis like half power beamwidth, some other nulls and all, we can calculate. It's very difficult to calculate in the polar plot. So for that, we can analyze these things in the linear plot very nicely. So another is the antenna field region. So in antenna field region, so there are one is reactive near field region, that portion of the near field region immediately surrounding the antenna at a distance of r1, that is 0.62 root over of d cube by lambda square. And after that region, the near field region, it's called that region field from the antenna between the reactive near field region to the far field region. And far field region is the that is the R2, that is 2 discover lambda. So D is nothing but antenna dimension, maximum antenna dimension. So actually we want that we are more interested in far field region, because so how much the far field region 2 discover lambda, that is in that region will keep our receiving antennas, and for long distance communications only we want this antenna. But so that's why this far field region we will be more interested in the far field region for this antenna. So next is the directivity. So directivity, the ratio of the radiation intensity in a given direction from an antenna to a radiation intensity average over all directions. Actually, if it's a isotropic, like one antenna, it's radiating everywhere. So compared to that kind of antenna, if your antenna is converging your power in one directions, so your directivity will be more, because it's showing the more directions. So if you see this figure 21, so if the dotted line, it's radiating, if one power you are sending, it's radiating everywhere in that in this from this antenna. But if one antenna is radiating only one side, so its directivity will be more. So actually, as per your requirement, you can choose your more directive antenna or less directive antenna. So if it's a if you want a communication like it will cover a total area in your locality, so that time you want to go for low directive antenna. But for your long distance communication, point to point communications, that time if you want a high directive antenna, because it want more area more distance to connect. Next is antenna gain. Antenna gains is the that is the maximum radiation intensity to the maximum intensity from a reference antenna with the same input power. Like for gain, we want a reference, like one reference is required. So how much reference power from the same input power? So from that your antenna, how much it is radiating, so that ratio you can get a gain. So for this gain measurement and all, you need a standard gain antenna. Otherwise, the gain measurement is not possible. So another gain relations with directivity, that is G equal to K into D, and K is called the radiation efficiency factor. Actually, this K is nothing but how much that radiated power from your antenna and how much you are giving that input power. So this K is depend on that antenna characteristics. If it is a horn antenna, if it is a dipole antenna, the K it will be changed. It will be changed. And so from K, so gain also related to this directivity. And another relation for this gain is 4 pi AE lambda square. A is called the effective aperture. Actually, in antenna, if the all section it will not be responsible for transmitting or receiving. So how much area it is responsible for the receiving or transmitting, that is called the effective. So like that, how much that effective area that this antenna is working. So like that, gain we can get that effective area. If it is more, then gain it will be more. So you can tell that if the antenna size if you will increase, then the gain also it will be more. Next is the antenna polarizations. So antenna polarization is very important. Like when your antenna you are exciting, so that time that electric field lines also it is coming. So how the electric field lines it's oriented with reference to the ground. Otherwise, when that if you are sending a signal in the receiving side, that nobody can get that in which orientation the electric field will coming. So in that way, they also make some arrangement so to collect this electric field. So if it is a vertical electric field is vertical with this ground, this is called the vertical polarizations. If it is in horizontal with the reference to the ground, it's called the horizontal polarizations. So if you see the dipole antenna, it's a horizontally if you keep, because electric lines it will be like that for in dipole. So this is called the this is called the horizontal polarized. And vertical polarized, if you electric field lines you are keeping in vertical, because if you change your antenna orientations, then only you can get the electric field also it will be changed. So this is a vertical polarization. So it is horizontal polarizations and vertical polarization, both are called the linearly polarized. Like it's linear in nature. But another is the circularly polarized. Actually, in circularly polarized, the polarizations that electric field vector it's rotate. So when it is propagating, it's rotate. So in it's not required to keep any arrangement. Like in any direction, if you keep your antenna, that you can get the signal. So like our mobile phone, so in any orientation when you are keeping, sometimes you are talking with in standing mode, you are talking it when you are sleeping mode. So everywhere you can get your signal. So if it is in any directions, you can get the signals. So another is that co-polarizations and cross-polarizations. So co-polarizations means when both the antenna is the same orientations. Like if the electric field how it is sending, and in the antenna receiving antenna also you are keeping in the same orientations. So the electric field will very nicely it can receive the signal. So and cross polarizations, if you are not keeping in the same orientation. So like it's a just 90 degree out of phase, then it's called the cross polarizations. So this co and cross polarizations, definitely in cross polarizations you are getting very less signal compared to the co-polarizations orientations. So next is the microstrip patch antenna, because initially I told that it's a very popular because it's a lightweight, low profile, and very in all the handle device you can easily integrate. So this antenna concept is 1950s and 1970s. This types of printed antenna has drawn more attentions in this field of antenna technology. So there are different kind of geometry like rectangular, circular in figure 23 it's showing here, and each and every having some its different character. So this antenna also capable for multi-functional facility like broadband, multi-band, linearly polarized, circularly polarized, high gain, stable radiation pattern, low cross polarizations level. So so that's why this microstrip patch antenna is very popular. So if you see these constructions, it's in the this yellow lines both are in perfect electric conductor, and this is called the patch, and this is the ground plane, and in between the substrate it will be there, and from here you can feed, or in another way also you can feed this antenna, and this two side, due to the fringing field effect, the antenna is radiating. I'll discuss how the radiations is coming in that microstrip patch antenna. So this is the basic structure, and this is the electric field distributions on the patch, and this is the fabricated patch, how it will look like. Actually this patch antenna is very easy to fabricate, and it's very lightweight, but one disadvantage is that the gain is very less. You can't put more power in that microstrip patch antenna. So that is the one disadvantage. For in another purpose, if where the more power and more gain is not required, that position we can easily use this microstrip patch antenna. So this microstrip patch antenna, it can also show a broadband and narrowband response. Actually, when you will send the signal to the patch, this is called the incident signal, and if it is a mismatch, it will reflect back. So some band it will match, some band it will not match. It will depend on the patch, how you design the patch. So it will depend on the patch. So one parameter is called the S parameter. So in S11, that is from one port 1 to 1, how its character, it we can easily get in this. We can plot in the S11 frequency versus S11 plot. So in S11 plot, you can see that this is a narrowband response. Like it's like is below this minus 25, 30, 35, below minus 10, you will get less reflection, means the antenna is more matching. So from here, look, this minus 10 if you will consider, so the band is very less compared to here, then 15 megahertz, like that it will come 4.6 or 7, like that, in around you are getting very less band. But if you see a broadband response, so it's coming 4.2 to here some 9 gigahertz. So the band is very more. So as per the design, that in different way you can change its character, you can get this broadband response of the patch. In the same way, you can also get the multi-band response from the patch. So look, this is the minus 10 one reference level, because actually minus 10, below the minus 10 you are getting less reflection. So if you consider this minus 10 a reference level, so below that minus 10 you will get that antenna, it will work very nicely. So look here, one band here, one band here, here and here and here. So 1 2 3 1 2 3 4 band you are getting less reflections from the patch. So different shapes like slot, slit cutting, U shape, E shape, and feed line modification, you can get this kind of broadband and multi-band response from a patch antenna. Okay, so now see this how the radiations is coming from the patch. So look here, this is the patch and this is the ground plane. So up to here, when you will excite this patch antenna, this is the electric field distribution, it will be look like that. So when from this end, when the discontinuity will appear, some electric field lines it will start bending, and it will going through the air also, and this side also it is coming like that, and it will coming here also. So this two side, the electric field lines is coming to the air also. So now look here, this vertical component of the electric field, this is the vertical component of the electric fields. So this is the opposite sides of the two edges. This look, this orientation of this electric field, this one and this is the opposite in directions. So hence it is getting cancelled out. And the horizontal component of the electric field, like look here, it is going this one, so we can write this tangential component, or it is going downwards, so you can get this, we can make this. So this and this, it will add up. This horizontal component will add up, and you can get a broadside, you can get a radiation in this size, this direction. It's called the broadside direction. So this is the if you see that this is the broadside directions. So here you will get a broadside direction, but this side and this side is in the opposite phase, it will cancel out, so you will not get very you will not get any signal in this side. So that's why this antenna is very popular. And one thing, this radiating slot, it's called this two width, it's called the radiating only. In lengthwise you will not get any radiation from this microstrip patch antenna. Okay, so this is a general one 2.97 gigahertz one antenna. When you are excite, this is a E-plane E-plane, and this is the co and cross pole radiations for the dipole one microstrip patch antenna. Look, this black line is a co-pole, and this is the cross pole radiation. So look here, from co to cross, the signal level is very less. So this is a 3D radiation pattern, and from there you can get that red one is the maximum power. So maximum power is matched in the forward directions, and you are getting a very good radiations. So and here that due to this ground plane, so look, this ground plane is very big. So this ground plane, it's stop the radiation in the backward direction. So this, we are getting a very maximum power in the frontward directions in this microstrip patch antenna. That's why you are getting in the 3D pattern or in 2D pattern also, you can get this the frontwise directions. You are getting a more pattern from this microstrip patch antenna. So some other technique, like if you use some aperture on the patch, if you make some cutting in the ground plane, so that time also you are getting a broadband response from a patch antenna. Actually, it will depend on the path length. So how much path length is it's covering. If you see, this is the length that so this is the length for current will flow, and if you use another cutting in that in the ground plane side, it will also travel in another path. So this two path, it will add up and it will excite in the lower side sections, and you will get a broadband response. So look here, this green line you are getting, look, it is below -10. So you are getting very broadband response compared to the other kind of structures. So look, this green line, if you see this 4.61, and it's a very good habit that because when you are using this antenna for a broadband response, so anyone can use for lower band side, or anyone can use from higher bands, and which you are given in your specification. So you have to check each and every band, so how the radiations is coming. So if you see the 4.6 gigahertz, so the radiations is coming very good, because near to that antenna you are getting very good radiations. Next is it's a 4.96, like in near to 5 gigahertz. And also the in the broadside directions you are getting very good response. It's a 6.63. You are also getting very good response, and it is at 7.6 gigahertz. They are also getting very good response in the broadside direction, because when you are making your antenna, if in the front side you should get a very good gain and good radiation patterns, then only the antenna will be very good for real lab applications. So it's a very good habit to check each and every time for in broadband response broadband antenna. So in everywhere in the total broadband region, how the radiation pattern is coming. So next is antenna for multi-band response. So look here, some different slot, so different slit and slot cutting that it has made, and so different slot cutting and different slit cutting, the current will it will flow in different path, and the antenna is resonating in different frequency. So look here, this antenna, this structure, in this structure that we have got this one antenna is resonating at lower frequency 2.5, 3.5, next 5.5 and 5.8, like that. So different band you are getting, and also you need to check that these are the band where we are getting the resonating frequency. So how the radiations is. So here we can see that radiation pattern wise, that you can get also very good radiation pattern, because in broadside direction you are getting very good response from this antenna. And these are the different resonating frequency and the bandwidth, and this is also applicable for our standard applications. So like 4G LTE, industrial and medical standard, this band WiMAX, then WLAN. So what are the requirement is there? So it will match with this requirement. Okay. So next is 5G communication technology. So as we know that that antenna we can easily use that low profile antenna, this 5G this microstrip patch antenna, or if you use some different kind of antenna, it will be in low profile, because everywhere it should be a handle device is required. So definitely we want the antenna should be very easy to fabricate, and main thing is that it is integrate in your system, in your handle device, that is your mobile phones and all. So first we will see that 5G communications, how the development, so how the 5G communications are giving a very fastest things compared to the existing 4G LTE or 3G, like that. So if you see the history of the last 50 years, this first generation, second generation, third generation, fourth generations, like that. So it has 1970 and 80s, that analog phone, that one generation computers, it was there. In 90s, that 2G it has come, and its speed is nothing but 40 kbps. Only the text message and so all that we can able to send. But in 3G, when it is coming the 3G, they are using this multiple input, multiple output, and packet switching for the data. And it's okay, it was okay, but speed is 7.2 mbps maximum speed was there. So now come to the 4G. It's like our computers. In 4G, it's like our computer in our hand. So its speed is like 50 mbps. So and WiMAX and all IP packet switching and ALT, long-term evolution. So all the things they are integrating, but still there is some problem in the 4G. So what about the 5G? It's coming in this upcoming this year. We'll see this. So in 4G technology, what is the limitations that we are getting in the 4G? So in 4G, as we observe that nowadays different applications, still we are using the 4G LTE. So different applications, like with mobile phone, we want to connect with our wristwatch, we want to connect with our webcam, we want to connect our CC camera, we want to connect with our another phones. So different applications are there in the 4G communication still that we want this. And day by day, that it's more user is getting user number of users is getting more and more and need more data. So it's very difficult to serve in this 4G technology. So in 5G technology, it's a next generation wireless and it's a 10 times faster than 4G LTE. And that it's telling that one HD movie will download under a second, and 5G will use a new radio called a millimeter wave. So this millimeter wave, that is a different frequency allocations. So in that frequency allocations only you can get this kind of huge data to download, or you can access this. So this upcoming 5G technology, they are telling that this the Internet of Things and virtual reality, autonomous vehicles, and other, like your coffee machine you can easily access from your remote locations. You can access your bicycles. You can access the drone from the remote locations. And Internet of Things is nowadays is very popular. So these are things all that it can cover using this 5G technology. So this 5G technology consists of that is 1 millimeter wave, small cells concept, massive MIMO beamforming, and this is a full duplex system. So we'll see that what is a millimeter wave. So as we see that in 4G, they are more crowded. Like we want to access the coffee machines, you want to access that, you want to control your drone, you want to access your autonomous car, GPS, Wi-Fi, C-band satcoms, S-band satellite receiver, all the things we want to integrate. So this 4G, that band is very difficult to serve in this band. So it has just shifted to the higher band because it has less utilized. People are not using in this band. So it's at the millimeter wave range. So higher frequency waves carries more data, and millimeter wave can support that multiple input, multiple output, this antenna, and it's a more bandwidth for all, and it's a new band. People are using very less. So that's why this millimeter wave, that new frequency band, it has proposed in the 5G communication. But it's not like that 5G. It's like below 6 gigahertz, all the band it will work, and some application it will go to that higher frequency band. That is for video downloading, that accessing like your your database and all. That will be for millimeter wave. So now let us see the small cell architecture for the small cell concept. Actually, when we will go through that in higher frequency, there will be more attenuations. So, and millimeter wave cannot travel through the building due to these higher attenuations. So it will absorb by the tree and the raindrop. So suppose this is one situations that 4 mobile phones are there, and there is no obstacles. So you're sending the millimeter wave in this way. So it can easily access this 4 mobile phone. So but is this not the current scenario? Because in current scenario you can get that different buildings and different trees, rain and mountains, so many things it will be come into the pictures. So if this is the current scenario, that with different buildings and trees are there, that time you can't access your phone from the remote location from your BTS. So what is the solution? So you can use a small cell concept, because you can make some small cell. So that cell it will connect with the BTS, from where it will be line of sight communications. So from that small cell concept we can easily access the phone. So this is called that small cell concept, because in 5G communication people are telling that in your nearest to that light post you can get your access. So this is the concept. And one advantage is that due to this near to that antenna, so the antenna power, it will be very less, so there will be no health issues. Like if you want to excite, pump the more power in that antenna, there will be no issues in that way if you use this kind of small cell concept. So now let us see the single input and single output, and multiple input, multiple output. And let us see that 100 Mbps data, if you want to send to the another end, and this 100 Mbps data, it will receive in 100 seconds. Okay, so in CISO, but in if you use this 100 Mbps data, if you divide 50 milli Mbps and 50 Mbps data, if you use this kind of construction like two transmitters, and the receiver also, it will be the same, and you can use a DSP processor, you can integrate and you can retrieve the data. So this data, it will receive this 100 Mbps data, it will receive in 100 in 50 seconds. Okay, so this is the concept of multiple input, multiple output. So using this multiple input, multiple output, the data rate, it will be improved. So instead of this two antenna, you can increase more and more antenna. So that same procedure, it will be getting you will get more achieved. This data rate, it will be improved. So 2x2, 4x4, 8x8 antenna array also you can use to achieve this high speed data communication. So this is the main things about this MIMO. So massive MIMO is like when you are using more than 10x10 antenna, then only you can use a you can tell this is the massive MIMO. So this massive MIMO, if you use, then definitely the data more. Excuse me. Okay. So antenna array more than 10x10, that's called the massive MIMO. So what about when you will make this massive MIMO in your existing antenna, existing system? So if this is the 4G tower, and in this 4G tower, you can, if you will go for this higher frequency, then the antenna size is inversely proportional to the frequency. So when you will go for this higher frequency, the antenna size will also less. So the same structure where the 4G tower is there, here you can easily integrate this 5G tower. So there will be no issues of any other extra space. So as the antenna size, it will be very less. So using this massive MIMO, you can easily attach this massive MIMO in the existing 4G mobile tower. So in that way, multiple MIMO antenna you can easily make, and you can get a high speed data communications. Okay, so beam forming. So here one more advantage is there in this 5G communication, that is called the beam forming. In 4G communication, when the antenna is excited, a single beam, inside a single beam, you can get a different user, like user A, user B, user C, like n number of user, it will be there. So if more number of user, it will be coming into the same beam, there will be a conditions. So you will not that time you are not getting the signal. So so there will be interference in this, in the that 4G communications. But in 5G, there is a multiple beam it will form, and every user, it will get a single beam. And also when the user will move, the beam also it will steer, because in antenna array, you know that beam also we can steer. And so it's a fast data rate, more number of beam forming leads the less interference and less energy consumptions, and beam forming makes the transmission more directives. So this is on one for 5G BTS tower that is in testing mode, and as using the array technique, that you can easily form the beam. Like in this case, we want a narrow beam, and also the beam will also it need to steer. So using this antenna array technique, because number of antenna we know, we can get that in antenna array, that beam you can easily form. So number of element, if you increase that, you can that beam width also it will be very narrow. So how much beam width is required, that we can easily make using number of antenna elements. And also the beam steering also we can make using the different phase angle change of this antenna array. So the beam also we can shift, and where the user it will move, that beam also it will move. So dedicated beam also we can put for the on a single user. Okay, so now the main important thing is the frequency band, because which frequency that we can use for this 5G. So one frequency band is called the sub 6 gigahertz, that is below the 6 gigahertz one band is there, and another is that is a millimeter wave, that is 24 to 100 gigahertz. So this two frequency band, that is decided for this 5G communications. So in India, that is 3.3 to 3.6 gigahertz. That is the mid band. That is a three band is there. The 700 megahertz they are not using. The mid band, that is 3.3 to 3.6, and the higher band, that is 24 to 27 or 27 to 29, like that, or 27 to 43. These are the band that in India, but in different countries they are the different frequency band they have also decided. It will depend on the local authority also, that which band, but general thing is that the millimeter wave should be there, and one band should be in the sub 6 gigahertz. The two things it will be same. Otherwise the mobile phone market, it will be very difficult to, like everywhere the mobile phone, it's not that made in only the in the origin country. So in different country they can bought, and for that the standard should be there, otherwise it's very difficult to access this phone. Okay, so these are the different MIMO antenna that people are doing research on that. So here the four element one MIMO antenna is the first one, and the second one is there is some 12 antenna MIMO antenna is there. So if you know that now you can get that if the number of antenna it will be more, then you will get a more and more speed. So and these are the different orientation people are using the MIMO antenna, because that antenna in that way you have to make that it will be very isolated from one antenna to another antenna. Then only that operation, that individual things like our this MIMO operation, that separately we can use this antenna. The data it will be divided, and the antenna, the receiver and transmitter, it will be the different. And once it will receive, then using a DSP processor, you will get the main data. So the antenna orientations and all, look here, the antenna orientation it will be different. So different, for that it should be isolated in this way. There are different diversity performance or diversity parameters are there that to check that antenna is working or not. These are some ECC, like some TIR at some other, I forget the thing. Some there are different diversity performances are in MIMO antennas. So that when we are going to design this antenna, that time we need to check this. There are different diversity parameters, and from that you can get that how that antenna is isolated or individually it is working. Okay, so in 5G frequency band, there are some name of this band is already proposed, that is N77, N78, N79. So in India, N78 people are using, that is 3.3 gigahertz to 3.6 gigahertz. Instead of 3.8, in India they are using 3.6 gigahertz. And this above 6 gigahertz, above 6G band, that is millimeter wave, that is N27, 257, 258, 261, and N260. So actually this high band, it's still now it's in the research way. The people are doing still research on that. So actually when we are going for this higher band and all that, each and every mobile phones and the BTS tower sections and all, it will be more costly. It will be more costly because in higher band all the components and all the system and all, it will be very difficult and very costly. So initially the people have started that, okay, we will start this N78 band 3.3 to 3.8, 79 band or 79, 78, 79. And we can use a MIMO system, and you can get a very good data speed. Instead of single antenna, we can use a multiple antenna to get a good data speed. If you see a prototype of this one Qualcomm, that is on 5G millimeter wave antenna, look, it's they have made a prototype in, I think in Asus, they have use this make an antenna, this Qualcomm, and this is that antenna. They have used this part and this part, and the size of the antenna is very less compared to this our sub 6 gigahertz. And this is that and prototype they have made. But if you see in that in the market, people are telling that is the 5G antenna, 5G mobile. So in the 5G mobile band, as one Realme on 5G and 5G said, as I have observed that in 5G band they are using this N77, 78, that they have already mentioned here that it will work this India and international, because they are selling in that antenna in India. So only this band, so they are not claiming this band like 257, 258, 261, 260 like that. They are claiming only that this phone it will work in 78, 79 like that. So from that you can get, these are all in sub 6 gigahertz, all are this phone it will work. Only thing is that the technique they have used on MIMO, so multi-user MIMO, so that is very high speed compared to this our existing 4G LTE system. So MIMO antenna, that also you can use for this your Wi-Fi or Bluetooth, sorry, in Wi-Fi or WLAN. So that time also you can get this antenna, this microstrip patch antenna. This is look here, this four port they have already assigned, because inside the four antenna it will be there. That is here also it is written that 4x4 MIMO sector panel antenna. Okay. So here also in 2.4 gigahertz and 5 gigahertz patch, this is also like four antenna. These are some data sheet I have collected from in that what is called uh, in their company data sheets. So and this is a massive MIMO, like what I tell, that is the more than 10 cross 10 or 10 cross 10 like that. So so this massive MIMO, this look here, the number of port it will be more and more. So this is a massive MIMO for MIMO antenna, because this massive MIMO they can use in that BTS section, and our antenna it will maybe 4 element or 6 element. That time also we can get a very good speed also. In that way you can also make this 5G communications or MIMO antenna system. So as in conclusions, that this improved 5G technology, so you can use an infinitely connected in the universe, and universal and ultimate access to information, social interactions, and entertainment in the future will expand, would expand and channel our lives in the new directions. So in government and authority may create a healthier setting using these innovations as a tool for a good governance, with which definitely encourage the investment in the 5G technology. As I already discussed, that this healthier setting, like the power should be very less, otherwise it will affect, it should not affect our health. And the speed gain, obviously it will be very like obvious, the indicating that whenever you go you have the access, like our home broadband connection for downloading or uploading any files, play games, or downloading movies and all. So generally, so this 5G technology is very useful, I think that in upcoming this days. So So people are also working on this 5G antennas. People also working in this 5G circuitry, that how to improve all the things and all. And so, okay, I think that these are the different reference that it will help me to make this presentations. So there are different books, very good books also is there for this. The first one, this Vizor book, it's very array and phased array antenna basic, that helped me to that radiation mechanism of the antennas and all, and other Balanese and this KP Roy, the Halvartis. These are the four good books for and this wear and microstrip patch antenna. So okay, thank you.
Thank you, Professor Sarkar, for your presentations related to that basics of the from the basics of the antenna to the advancement of the antennas, which will be useful for the 5G technologies, and mostly the MIMO antennas will be useful for 5G technologies. So I have one question. Before that, I would ask the participants, please raise your hand to ask the questions to the presenter. We'll unmute from our side. My question is, so using which simulation software you have designed those antennas?
Okay, actually, this HFSS software I have used because every industries and all, they have using this HFSS software, and this software that results are very matching with the when you will go for fabrications. So so better will go for HFSS. People are using CST and other software also, but is all softwares are very good. But in our in my things and all the things I have designed using a HFSS software.
Okay. So mostly that MIMO antennas need more than 2 ports, 4 ports. In your case, you have shown.
Yeah.
So from where it says, suppose I want to design those antennas, fabricate those antennas, and want to measure those characteristics of the antenna.
Okay.
So from where we can that measurement? Actually, measurement facility is not available everywhere. So from where you can suggest somewhere that we can take.
I think that in some and IITs and all, they having the facility. So and in Samit, Kolkata and Samit and Chennai, Mumbai, they having this facility to measure this basic. If you want the basic things and all, that also make. And also the for MIMO antenna, when you are considering that couplings and all, that also you can measure, because when you are design this MIMO antenna, there are different directivity, some diversity properties that you need to measure. So that time, I think that they can help you to design this kind of facilities and all.
So another question before others will ask. So what type of substrate you are using? Means that you can generally use that PTFE or FR4 epoxy. I would say that FR4 epoxy or Arlon. So which substrate will be better for this designing, or less loss or less as compared to others?
Yeah, actually, this substrate, first of all, that antenna should be work properly. So for that, we want that the tolerance of this substrate, and it should be low dielectric constant. That for that we can go for that RT duroids and all. So that RT duroids is very costly, because that all the parameters and all, it will be very appropriate, and the tolerance level is very good, and that losses are very less. So that artiduroid and other component, other substrate also we can use, as per that how much your response it will give. That is very important. Like if you want like 2.2 instead of 2.323 also you can use, but as per your availability and all, that also we can also to check that, but it will work, it's not a problem.
Okay. Thank you, sir. And other participants, please raise your hand so that we can unmute yourself. Abhishek sir, would you like to ask something?
No, okay. That's a very nice presentation.
Okay, thank you, sir, for your valuable time and wonderful presentations and some basics from the antennas characteristics and also that advancement in the designing of the 5G technology. So, thank you, sir, once again for providing us the opportunity. That,
Thank you very much to the organizing committee, and thank you, Dr. Abhishek Das, for giving me a chance to give a lectures in this FDP. So thank you once again.
Okay, sir. So, with this, we are concluding today's lecture session. So, on tomorrow, we have two more presenters. I would say that eminent speakers are there. Those will discuss the different aspects of this 5G microwave and millimeter wave communication. So, I would request all the participants to be present at 2:30 on tomorrow. Thank you, sir. You can stop presenting and okay. Okay, thank you all for your valuable time.